Here are solutions to homework set number 7 for ECE 463, Modern Control. In this homework set, we're looking at servo compensators. Now, the first problem is actually not using servo compensators. It's using our regular old full state feedback. So I've got the input is some gain kr times r minus kx times x. Same as we did in homework set 6, find kr and kx so the DC gain is 1. So the trick is input the A matrix, B matrix, C matrix, do pole placement. I want 5% overshoot for step input, 10-second settling time, place the dominant poles. Other two poles go somewhere. There's Kx. Checking the eigenvalues. Yep, Kx is right. Pick Kr to make the DC gain 1. Now try it. So here's the control, the calling routine. I set the initial conditions, have the full state feedback gain, Kx, Kr. My set point just goes plus minus 1, and my feedback control law. If I try it, here's what happens. I start at minus 1, I tell it to go to plus 1, and it does. There's a little bit of overshoot because I designed my closed loop poles to have 5% overshoot. So everything seems to be working. This is for the nominal system. This is with the mass of the ball of 2 kilograms. And so again, if everything's nominal, everything's fine. Designed for DC gain 1. DC gain is 1. I hit the set point. What if the dynamics are wrong? So if I go over here in beam dynamics, I can set the mass of the ball. It's supposed to be 2 kilograms. Change it to 1.5. I'm actually going to make it 1.9 because 1.5 made it go unstable. If I make it 1.9, now the ball's not as heavy as it should be. The torque on the beam that I'm expecting isn't as large as it should be. So likewise with this control law, I missed the target. That's a constant steady state error with a constant disturbance. And again, tell it to go to minus 1. Again, I miss. That's because effectively there's a constant disturbance. The torque is force times distance. The force is related to the mass of the ball. The mass is 0.1 kilogram less than it should be. When the dynamics are off, the DC gain is off. Pretty much everything's off. So, how do I fix that? Well, that's where you add a servo compensator. What the servo compensator does is I integrate the difference between the output and the set point at steady state. Almost by definition, the states are 0. If I integrate that difference, and z is a constant, then this guy right here has to be 0, meaning y tracks r. What the integrator does at the output, that forces the steady state gain to be 1. It forces y to track r at steady state. If it didn't, z would increase, and I'd be increasing the input. Or if it's negative, z is decreasing down, change the input. Essentially, the servo compensator finds what constant do I need to bias the input to force y to track r. And that does two things. I track a constant set point, and I reject a constant disturbance. Again, this is whatever constant it takes to hold the output. Now, when you do that, I have a 4th order system for the plant, a 1st order system for the servo. I now have a 5th order system. Mathematics could really care less. I've got a 5th order system, use pole placement to place all 5 poles. So what I do is I create the augmented system. That's your A, 0, C, 0. Here's the servo compensator state is an integrator. My B matrix relative to U is the B matrix for the plant plus 0. B matrix with respect to the set point R is 0 minus 1. Now use pole placement. Put the closed loop poles wherever you want. I chose 10-second settling time, 5% overshoot just to be consistent. And other poles 2, 3, 4. I get my 5 feedback gains. The first 4 are Kx. The last one is Kz. That's just because that's how I define my augmented system. For the linear system, I can check the linear step response, find the feedback gain, or the step response of A minus Bk, the step response with respect to R, C, and D, plot the step response, and here's what I get. Step response with respect to the disturbance, change the B matrix. If that's the B matrix with respect to U, that's over here. That's my disturbance. I should reject a constant disturbance, and I do. Now for the nonlinear system. For the nonlinear system, I have to modify the code a little bit. Instead of having I've got Kx and Kz. My servo state, I'm going to start the integrator at z equals 0. And then my control law is now minus kz times z minus kx times x. I've got this extra state, the integrator, the servo compensator, that whose input is the difference between the output and the set point. Integrate x, integrate z. And in this case, I have the mass is 2 kilograms, like it should be. I tell it to go to plus 1 meter, and sure enough, it goes to plus 1 meter. And that's no different than what we had before, so that's not real impressive. Tell it to go to minus 1 meter. It goes to minus 1 meter. So again, not a whole lot different than what we had with just full state feedback. Where the servo compensator shines is what if there's a constant disturbance? We'll let this settle out at 30 seconds. Suppose the beam dynamics are wrong. Let's make this like 1.8. Now before it wasn't going to track, but what the servo does is it says there's a constant disturbance. That's the mass that I'm missing from the ball. Keep integrating. Figure out what the constant torque has to be to hold the ball at 1 meter. And it's going to keep on integrating until the error is 0, until you're actually at 1 meter. So that works if the ball is a little bit too light, by 0.2 kilograms. It also works if the ball is too heavy. So let's try the other way. This wasn't asked for, but just for fun. If the ball is too heavy, now the integrator knows I have too much torque. I have to add extra torque to counteract the force due to gravity. And there it overshot because the extra mass caused the ball to, or the beam to go down, ball to go too far. The integrator eventually figures out what you have to do, and it brings the ball back to your set point. That's what a servo compensator does. With the integrator, I force the output to track a constant set point. I also force it to reject a constant disturbance. So that's problem number 2. Did that. Now, a problem with the current solution is it tracks a constant, but it does not track a sine wave. Again, let's go back to MATLAB. Change the set point to sine of 0.6 times t. If I have a sine wave rather than a constant, and let's bring it back to 2 kilograms, nominal case. I can track a constant, but I have a hard time tracking a sine wave. So there's my sine wave, that little x going back and forth. If it was a constant, I would hit it, but this isn't a constant. And you kind of see that it's just doing a really lousy job, almost completely out of phase. How do you track a sinusoidal set point? Well, that's a slight variation on the servo compensator. A constant integrator tracks a constant, have the eigenvalues of az at plus minus j.6. Now I will track a sine wave at 0.6 radians per second. And kind of how that works is this essentially has infinite gain at 0.6 radians per second. If you do the transfer function, it'll be something over s squared plus 0.6 squared. At 0.6 radians per second, this is 1 over 0, gain's infinity. Infinite gain means the input's got to be 0, so that 0 times infinity is a constant. That integration constant is how much cosine, how much sine do I need to apply bias the input to force the output to track. So it's really the same procedure as before, except that now I add dynamics to the servo compensator. This is any system that has poles at plus minus j.6 radians per second. This is one way to do it. Have 0 on the diagonal. Off diagonal is your frequency, plus 0.6 minus 0.6. The B matrix is anything that's controllable. 1, 1 works. The augmented system now has 6 states. 4 states for the plant, through here, and 2 states for the servo compensator. So here's AZ, here's A, and this is BZ times C. The B matrix with respect to U, B matrix with respect to R, the set point. Now use pole placement. Place the closed loop poles somewhere to meet your specs. This gives a 10-second settling time. Other poles somewhere out of harm's way. I have my 6 feedback gains. The first 4 are your gains times the states, Kx. The last 2 are times your servo, Kz. Then to implement it, for the linear system, I'll take the step response of the closed loop system, and here I'm using the step 3 command because I want the input to be a sine wave. MATLAB doesn't have a sine wave input, so I've got to create that function. That's step 3. Give it the time points. My initial conditions are all 0 for this homework set. My set point is a sine wave, and sure enough, it tracks a sine wave. If I have the disturbance, make the B matrix with respect to U. Here, this is the disturbance. If my disturbance is at 6 radians per second, the output goes to 0. It still tracks the set point, R equals 0 in this case, and rejects the disturbance. On the nonlinear system, so I have to modify the calling routine. Here's my feedback with respect to X, with respect to Z. AZ is now a 2 by 2 matrix. Poles are plus minus j.6. BZ is something controllable, and my servo has 2 states. My control law is still minus kz times z minus kx times x. The servo dynamics are now az times z plus bz times the difference between the output and the set point. Let it run, and here's how it behaves. My set point is a sine wave going back and forth at 0.6 radians per second. There's a transient as it tries to figure out what is the input. What does the servo have to input sine and cosine to get it to track? And eventually it figures it out. And there's tracking nicely. So there it tracked a sine wave. Suppose instead I make this a cosine function. Really makes no difference. It will track any set point that is 0.6 radians per second. So it's starting to lock in. Here is getting smaller. And there it nailed it. So that's the servo compensator. If you have a constant disturbance, or you want to guarantee that you track a constant set point, I can add a servo compensator with a pole at s equals 0. If I want to track a sine wave, add a servo compensator with poles at plus minus j omega, where omega is the frequency of your set point. The problem with servo compensators, if I change the set point, it no longer tracks. So the general case where I don't know the frequency of the input, that's leading more into adaptive control, a different course. I'd have to estimate the frequency at the set point. Then I can redesign my feedback control law on the fly. If I want to have this guy right here, time varying, well, that's adaptive control, different course. And kind of here you see that I just made a small change, went from 0.5 to 0.6 radians per second. It tracks dead on at 0.6 radians per second. It's missing horribly at 0.5. That's the problem with servo compensators. But anyway, that's homework set number 7 for ECE 463, Modern Control.